Hello everyone. Today we are going to learn about the merge sort algorithm. In the previous video we talked about the insertion sort and now we are going to talk about the merge sort algorithm. So let's begin. These are different things that we are going to cover in this video. First of all, we start a simple algorithm of merge sort. Then I will explain it with an example. Might be I will take an example previously then explain the algorithm and then again I will take another example to explain the algorithm in a much better way. Because it's a quite long algorithm, merge sort, so I'll try to explain with an example to get more clarity on it. Then we talk about some complexities, simple time and space complexity of it, and some properties associated with it. Okay, let's begin. So this was the algorithm of merge sort. So this is the part. This is the merge sort. This is the function. A is an array that has been passed. M is one indices and N is also one N indices that has been passed. For example, how like okay. For example, we took an array of size, let's say 10, 1, and the other elements are here. There is 10. Okay. So M corresponds to this indices and N corresponds to this indices. So M is the starting indices, N is the ending indices, and A is the array. And the idea behind the merge sort is that how merge sort works on a principle known as divide and conquer. So basically what it does, whatever has been given, it founds the list of elements. Let's say the array has been given, and it break the elements into two different parts. It divide and it do some functions independently. So it will perform some function here, and the same function will be repeated here also, and then it will conquer. Like after it will divide, it has this part and this part. Then again it will merge to one particular array itself. So it works something similar to this. It divide and conquer, the principle behind all of this. Then what it checks the whether m is less than equal to n. So let's say now m is always less than equal to n in this case. At some point of time this statement fails. I will come down when it will if statement fails. So 1 is less than equal to 10. Then we find the midpoint of it. Let's say the midpoint is here 5. So now z will be equal to 5. Okay. Then we call two different functions. One is merge sort. The same function we call it twice. We call the merge sort first of all initially a m to z. So from this part, from this a function has been called, this particular function, and again from this part this function has been called. So this is the first part, this is the second part. And after getting the results from that merge sort, we call the another uh, function that is known as merge, which actually merge these two subparts a m z. So from this to this it get merged. So basically this is a recursive algorithm which has been recursively called, and previously we talked about the insertion sort algorithm which is an iterative algorithm, and now is a recursive. Recursive in the sense it's called the function again and again and again. So it will call the function itself again and again merge sort, and also has another function known as merge. So before going to the merge sort, it will be better if we talk about what is merge, then I will come back to what is merge sort. So before learning that, we need to learn what is actually merge. There is a merge function. We learn first this and then we'll come back to what is merge sort. Now this is the algorithm of merge of it. So here also basically the array has been given. M is the size, initial size, Z is the middle point, N is the ending indices of it. Then it took some sizes, initialize some array, then do some for loop thing. It then at the end it places an infinity number, and then it performs some functions as a derivative. So if better going to line by line of this particular algorithm, let's learn it from an example point of view how it looks like. Okay. So this is the algorithm of merge that we are talking about. Let's talk with an example how this could happen. So starting uh, before I do one thing. Before taking this part, just I will give an example and I will come back again to this algorithm part. Let's have an example. Okay. So what we are talking about? We are talking about the merge. 1, right? So what does merge? As I said, let's say there is an array, okay, and let's say the array size is 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the array size is 8. Now, let's say we have some numbers here and we divide them into two different parts. Let's say this array we have this left hand side and there is a right hand side array of it. So 4 and we divide them equally. So as we said here, let's say the indices is starts from m, it has n, and let's say it is 1, 2, 3, 4, 5, 6, 7, 8. So middle part, this left sub part will come down to here. Let's say this z is the middle part of it. So from here to here, we copy it down into this array, and from here to here, we copy it down to this array. Okay. And z is the middle part. Z is the middle part. Then let's say we have again put in another array. Let's say we want to have this final array, which is the same as the size of the first one. So it is same as 8 elements. 1, 2, 3, 4, 5, 6, 7. Okay. Now what we will do, we take a, let's say the name of this left sub array is L. Okay. And let's took the right sub array as R. So the name of this. Then we take two pointers. The first pointer, let's say we take I, and this is J. So J is pointing to this, I is pointing to this. Now we do one thing. What we will do, we'll insert an infinity number at the end of both the left and right array. So let's insert one number here itself. So the number is, let's say so whatever the size of this array, we insert an infinity number at the end of the first subarray and the right subarray, left and right subarray. Infinity is it's suppose a very large number, so that's how it's a very large number. Why we keep this very large number, whether we can keep any other thing, let's discuss that on later point of time. Let's think of this. So we have a main array. We divide them into two subarrays, left and right subarray, and at the end of both the subarrays, we put an infinity number. We have two pointer. Is pointing to the first element of the left array. J is pointing to the first element of the right array of it. Now we have one more array which is the same as size of the initial array, and we took a pointer of, let's say, k here. We took a pointer of k here. Now what it will do, okay, I use another color to make it consistent. I use a k. So it's the main part, I use this k, and in this I remain as the same. Now let's take some numbers to understand it more clearly. Let's have some numbers. Let's say we have 4, 3, 9, 6, 2, 1, 7, 8. Okay, let's have this number. Now let's copy this number to here. 4, 3, 9, 6. Okay, and here 2, 1, 7, 8. Okay, now the task is to, let's say for I, what we will do, we'll check whether L of I is less than equal to R of J. Means if this number is greater than this number, what we will do, we'll copy this number to here. That means, let's say this is the main, let's say this name is A, we put down. What we will do, we put AK as L of I, and will increase equal to I plus 1. Sorry, I equal to I plus 1. And if this one part of it, and if else Rj is less than equal to Li, then what we will do, we put Ak is equal to Rj and we'll increment j equal to j plus 1. After doing this, we'll increment k equal to k plus 1. And this will run for how much time? 1 to the size of the array. So here this is 8. So for this amount of time, this particular algorithm will run. So how it will look? As I said, Li is greater than this. Then this is not. This is the correct one. It will run. So to if 4 is less than equal to 2, no, but 2 is less than equal to 4. So this is true. So this 2 will be copied here, and this j now will, and this k also, this j now pointing to this, and k will point to this. Now it will check whether 4 is greater than 1. No, that's also not true. Then 1 will be copied to here. Then again j and I will be incremented. So now j will point to here and k will point to here. Now check 4 and 7. 4 is not get 4 is actually now less than equal to 7. Then 4 comes down to this place. This part execute. Now I will be incremented. And subsequently k also get incremented. Now I will point to here and k will point to here. Now 3 is compared to 7. 3 is less than 7. So 3 will be here, and then I gets incremented. Similarly, k gets incremented. K comes to here, I comes to here. 9 is greater than 7. No, 7 is actually greater than 9. 7 comes here, and this j gets incremented, and subsequently also k gets incremented. Now 9 is greater than 8. No, 8 is greater than 9. So 8 comes here. So this uh, j comes to here. Now, and I will remain here, and k also move down to the next place. So now 9 is greater than infinity. No, 9 is not greater than infinity. So 9 will paste here, and okay, 9 will paste here, and say now I will get incremented, and 6 is greater than 5, so 6 will paste here. So the main idea behind of doing this is this thing. Okay, so that's how, and it will terminate. So 1, 2, 3, 4, 5, 6, 7, 8. 8 times it will run, and it will terminate. Okay. Now you might think that what is the purpose of doing this merging and all. Now I will take this. I will take a similar kind of thing. Now I will take another example of it. Okay. Then you will come to know how is this merging is so important. Now I'll do the same example 4396. Okay. Let me draw an array first of size 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Now what I will assume, since I divided into the middle part of it, I will assume this particular part is sorted in ascending order, and this particular part is sorted. Individually both are sorted. Okay. Individually, let's assume this both are sorted. So 4396, so 3469. Okay. So we put the numbers as 3469. So 3469. Okay. And here this order is a 1 to 7 8. Okay. 1 2 7 8. Okay, we have put up one more extra. Okay. Now the same thing, we this is the n, this is the n, this is the z, this is 1 10, this is 50. We put two subarrays. This is the first subarray, This is L equals to 1, 2, 3, 4, 5. Last one is the infinity. And there is a right subarray 1, 2, 3, 4, 5. Here what we'll put down 3, 4, 6, 9, and here we put down 1, 2, 7, 8. So what's the difference between the previous one and this? Previous one we have just divided, and now we put an assumption is that one side of the array is sorted, another type of array is sorted. So you can see this both the arrays are sorted, but individually, but they are not sorted uh, together. So they are not together sorted, but individually these are sorted. 2, 3, 4, 5, 6, 7, 8. The same size of this, and we put an I counter here. We put a J counter here, and we put a K counter here. And the previous algorithm now runs. Let's see. Now 3 is compared to 1. 1 is the smaller, so 1 comes down to here, and now K will get incremented as well J get incremented. J comes down to here, and K comes down to here. Now 3 is compared to 2. Now 2 is smaller, so 2 will come down to here. Now J and K gets incremented. J gets the part of this, and K gets the part of this. Till now, let's say put a counter, count equal to 2, and as I said, this will run to 1 to 8. Okay. Now here 4 is now compared to 7. Now 4 is bigger, so 4 comes down to here, and now K and I gets incremented. I gets here, and K gets here. 4 and 7, sorry, 3 and 4. Wait, so this one is 2. Okay, fine. This one is 3 because 3 and 7 will get compared. Now 4 and 7 get compared. 4 comes down to here. Now K and I gets incremented. Now K comes down to here. I gets this. 4, 6 and 7. 6 comes down to this place. Now okay, count is equal to 4 now. So 1, 2, 3, 4. Now this get incremented. Now K also get incremented. K comes down to here. I comes down to here. 6 and this. How many times this count is actually 1, 2, 1, 2, 3, 4, 5. This is not 4, this is 5. We have done. Now 9 and 7. 7 is smaller, so 7 will come down to here. This place to this. Count is 6. So K gets incremented, J gets incremented, J is here, 9 and 8. So now 8 gets 8 gets the place of here, K get incremented, and now J gets incremented. So it is 7, and the last 9 and infinity gets compared. 9 is smaller, so 9 plays down to here, and I gets here, and K gets incremented. So for now this is 8. Now since it will run for 8 times, so this algorithm turns down to this part. Now what difference you are observing? Previously we have done the same thing, now we are doing the same thing. Now this total array is sorted. This array was sorted, and this array was sorted individually. Now together, these two are sorted. So if we put an assumption or we put in such a way that when we took the left and right subarray, both these arrays are sorted, then if we do this merging procedure and we do this, the final array also gets sorted. So that's the assumption we are going to take. So basically this is the assumption and this is the payload. So let's now talk with the previous algorithmic part after taking this particular example. So we took this, let's say the number 34691278. Okay. We took another example here. Let's say we look it. Now let's go to this particular example and talk one by one about all these particular lines. This algorithm is the same I talked about. L is left subarray, right subarray. This was the algorithm that I was talking about. The left and right array. Now let's have this particular part. What is this? Now let's start with this. This is okay. This is M. This is N. 1, 2, 3, 4, 5, 6, 7, 8. Okay, here was 8, 1, 8, and let's say Z is equal to 4. Let's say Z. So this is okay. This is 4. Okay, to make this synchronize, we put this. This is 4, and this is equal to Z. Okay. Now we put Q1. What is Q1? We put down this Z minus M minus N, the size of the left array. So Z is was 4. 4 minus 1, 4 minus 1 plus 1. So left subarray size is 4, and Q2 is the size of the right subarray, that is n minus z. So 8 minus 4 is equal to 4. So now what we will get? We get Q1 as 4 and also Q2 as 4. Q2 as 4. Okay. Now let's move forward. Then we took two arrays. L is an array that we are taking, and we are taking R, right array. So according to the sizes, this is the Q plus 1. So 4 plus 1, 1, 2, 3, 4. And we took here also 1, 2, 3, 4. And we took another n plus 1. So we took another one which put as infinity. By now you might be able to guess why we took an infinity. Maybe now it will get more clear. Then we'll copy. So this for loop is 1 to q. So for this part we'll copy. This part will copy to here, and this part will copy to here. So here what will copy? 5, 2, 8, 6, and here 3, 7, 6, 9 will copy. Let's okay, directly we go to the assumption that we are taking 5286. So 5286 is what? Actually it is 2, 5, 6, 8. This is sorted. 3, and let's talk about this. 3, 6, and 7. Okay, 3, 6, and 7. Similarly, let's have this part. Let's see, and this is also let's. Okay, now this is what I'll come to the picture how actually we get this sorting. So let's assume this left subarray is sorted and right subarray is sorted. So 2, 5, 6, 8, and 3, 6, 7, 9. How we'll get the sorting part, that I will discuss in the merge sort itself. So there's a merging thing, but it gets the input of this thing. So it gets the input where this left subarray is sorted and right subarray is sorted. Now we took a point. Now we took another array of the same size of this, and we put this infinity infinity LDN now, and done. And now we are taking the one more array of the same size of this 1, 2, 3, 4, 5, 6, 7, 8. Okay, and as I said, I is from 1 to q1. So this is the I which will be pushed here. J is here and which will be pushed here. That's it. And now it is k, and k with a final array. It starts from m to n. Here 1 to 8. 1 to 8. It will put to 1 to 8. So now similarly it will compare 2 with 3. 2 will come down to here, and it will compare 2 with 3. So 2 is less than 3. So that's how 2 will place down, I will move it, k will move part, k, oh I forgot, right, it's k equal to k plus 1. Here one thing will come is equal to k plus 1. Okay, this thing will come, and now 2 will compare with 3, then again 5 will compare to 3. Now here 5 will place down to 3, j will get incremented. Now j will place down to here, I is placed down to here. 2 gets incremented 3, 2 comes here, 5. Now, okay, just a minute. Maybe I've done something. Okay. So 2 is compared with 3. So 2 comes here. So j is particular here. 5 is compared with 3. So 3 comes here. So yeah, I is here and j is here. Now 3 comes the picture, k is here. Similarly, 5 and 6 will compare. So 5 will be sitting here. We put 6 and 6 both there. If it is common, then we can, if the numbers are repeated, we can take any one of those to come first. So in this way, this is faster. There's an equal to 6 can come here, then 6 can 7, then 6 again come here, then it come to 7, then it will 8, and it will 9. So at the end, we'll get this particular array. So that's how this merging procedure is done. So in merging, we give an array of size something. We put the first index, we put the middle index, we put the n index. We took the size here of both the left array and right sub array. Then we initialize the left hand sub array with one additional plus one, that is put down to plus of one plus of one. Then we took you copy this. This is the copying part. So we copy the left part and the right part accordingly to the left and right subarray. Then the last part we put this infinity, and then put it infinity. And this is the part where we compare both the left and subarray and we copied them into again the previous array itself. So we can use the same array because since we have already copied down the element, so we can like delete all these entries of this particular array and we can reuse this particular part. So why I'm saying the reusing part, if you notice this, now let's discuss some properties associated with this particular part. What are different properties associated with this? So let's say the size of the uh, now let's say the size of the array is 10. And then we subdivide them into two. So this is the extra thing that we are putting down. So we put a left array of size 5 and put a right array of size 5. Now since they divided equally, so that's how 10 is the number. So it might have the, let's say, right part gets n and left parts get m. So if the array of size n, so we take an n plus m, and then it the space complexity extra space it is taking down. So it took some extra space. So whenever it depends on the input. So how big is this? It depends on the particular input, whether it is left or right. How big, how much big the left subarray or right subarray, it totally depends on the input. It cannot be predicted beforehand. It can be 1,000, it can be 1 lakh, or it can be 2,000, depends. So because you cannot predict this, so we have the order of n. So it depends on how much size it requires. So this type of algorithms where we need some extra space. In the previous one, in short, we have seen some temp I and j, so they are constant throughout the algorithm, independent how much size of the array is there. So that name is in place, and this type of thing is known as out of place. Whenever we require some extra space memory, which is not we cannot fix at the starting of this, so it is required out of place algorithm. Also, if you look carefully, the for loop it will run for 1 to 8 times. So this time complexity of this is actually order of n. So this time complexity will be order of n. So space technology is this, and time complexity of running of this, since for loop will run for 8 amount of time, 8 is the actual number of elements, so it is order of n. So merge procedure will take a time complexity of order of n and extra space, so it is out of place. And mind it, we are talking only for the merge part. We are not talking about right now the merge sort of it. Merge is a one call of it of the merge procedure, entire merge procedure of it. I hope the merge thing is clear now. How it is worked out. It is quite simple. If you look down, it's divide them and then do the equal part. Divide and conquer part. Now let's go back to this one. Here also one thing I missed out to write is here k equal to k plus 1. Okay. Now let's go to previous one. This one. Let's took this example and now try to understand how this is come into the picture. Okay. I do one thing. So basically, these are two defined functions that plays into the role, and why we need this kind of particular uh, type of thing is required because of the time complexity that we are going to learn. So every sorting algorithm has some particular properties associated with it. So with the particular properties, how can we able to extract whenever it is required? So depending on whatever situation you place down, you choose whichever algorithm you need to place it down here. That's it. So today, okay, okay. Now we talk about the merge sort algorithm. Now previously we talked about the merge. Now we'll talk about the merge sort. Okay. Um, this was the algorithm. Okay. Now let's talk about the merge. So this initially take an array of AMN. So let's draw an array again. I will just okay. I will do another kind of thing, which might be easy to understand in this, rather than taking an array again. Uh, Previously we talked about the array that was size of 8, right? talked about this array. We took an array whose size was 8. Now let's take an array 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. This is extracting it. Let's bring down to more, or we took in 6 array kind of thing. To understand this algorithm, let's do a smaller amount of size. So this is the six elements are there. Now what it will do? Now initially let's talk about it. I termed them as MS merge sort, and this is MS and this is merge. This let's look as M. Okay. Now let's talk merge sort has been called. It has been called from 1 to 6 initially for this particular line. Then it since M is 1 is less than equal to 6, it divides them into 3 defined parts. Okay. What was the first thing it is doing? It is calling from merge sort. It is calling in the array A from, let's say we divide them into three defined part, and the middle part is equal to Z. So from 1 to 3 it is called. Then here it is called from 4 to 6, and at the end it is calling merge on 1, 3, 6. Let's take Z equal to 3. This is Z, but we're talking Z equal to 3. Then this part is again break down to 3 defined parts. Let's talk this part, middle part has been break down. So let's take the middle thing as 1 and 2. Then this part is 3 and 3 merge, and then the merge procedure is called. So merge procedure, let's take it as 1, 2, 3. Okay. Then similarly this has been called down. This has been called down. This also merged down to 3 defined parts. Okay. Merge sort of 4 and 5. Merge sort of 6 and 6. And then merge of 4, 5, 6. Okay. Then we break down to again 1 is less than equal to 2. Then again we break down to 3 defined parts of merge sort of 1, 1, merge sort of 2, 2, and we merge 1 and 2 now. Okay. Now this is 3 is not less than equal to 3. This comes down, and this is merge of. Then we 4 and 5. Then we break down this into 3 defined parts again. Merge sort of 4, 4, merge sort of 5, 5, and then merge of 4, 5. Okay. This is the array that we have put down here. Now it will not break down to more because 1 is not less than 1, 2 is not less than 2, 4 is not less than 5, 4 is less than 5. This is how this whole algorithm that we can write down in a tree-type structure of it. Why I have written this in tree-type structure? We'll come down when we discuss about the properties associated with it. So we cannot break down to this. So if we have any element here, whatever element we have taken, let's say any element we took down for this particular part, let's say 4, 5, 6, 1, 2, 3. Okay. Then if we took this 1 and 1, so what we are taking for this particular 1 and 3, we are actually, this is the left array, this is the right array for this. And again for this, we can see if you divide this for this particular part, this is the left, this is the right array that we are talking about. Then again for this is the left and this is the right part. And for this part, so for specific thing, for this particular array, if we have an array of size 4, 5, so let's say we have an array of size 4, 5, we divide them into two parts, 4 and 5, and we have again a final array of size this. So now we have divided 4, 5, then we call a merge procedure. When the merge procedure is called from 1 to 2, 4 and 5 has been passed to this particular part, divide them into two parts, 4 and 5. 4 will compare it with 5, 4 is smaller, and it have this infinity part and an infinity part, and it go 4 and 5. Initially after this 1 and 2 has been called, if in case, okay, here we can take an example. Previously we took the assumption is that the these are sorted. Now we took an example 4, 5, 6. The assumption we are not taking now. This can be any order. Let's say 6, 5, 4, 2, 1, 3. This is not sorted. Now when this is not sorted, now let's anything we are taking. Now we relax the previous thing that we discussed. We took an example that this can be sorted. Now we took any arrays there which elements we don't know whether sorted or not. We just defined the array and now the task is to just to bring the sorted array at the end of it. Now left subarray, right subarray does not need to be sorted. They will handle it accordingly. So this part is 654. This part is for 6, 5, 4. We divide them into again 6 and 5. Then the 6 and 5. Then we divide them into ms equal to 6 and 5. So 6 individually, 5 individually, and it is given to the merge sort. The input of this 6 and 5 will be go to merge part, and it will convert them into 6 with an infinity and 5 with an infinity. And finally, we will have an array of the same size 6 and 5. 5 will be compared with 6. So 5 is here, 6 is here, and it will go down to this. It will eventually go down to this part of it. So at the end of this, mm, at the end of these calculations, what you will get, we'll have this 5 and 6 sorted. So after this part, we'll have an array which 6 and 5 are sorted. Now 6 and 5, 3. Now 3 is what? 4. Now this part will be given as an input to where? This part will be given as an input to this merging thing 1, 2 and 3. Now merging 3 is given, it will divide them into two defined parts. So let's say it divide them into, so it is 5 and 6, right? After it get divided, it is 5 and 6 actually. Okay, 5 and 6 it divided into two parts. So this part is the left array 5 and 6, and this part is the 4. We divide them with this and divide them with this. Again they have an array. It will again be compared. 4 will be compared with 5, 6. This will be compared. So after comparing all this, what will happen? We have 4, 5, 6. So after return, after this part is executed, what will we have? An left array of it. What does this left array does it mean? Here left array means the final part of, here left array means is the final part of the main array. So after calling this, we have this left array which is sorted. We have 4, 5, 6, and now it will similarly work on this, which gets an input of 2, 1, 3, back down to 2 and 1. Then here 2 will come, here 1 will come, and again it will break down to two different parts 4 and 5, and eventually after getting this we have 1 and 2. This 1 and 2 will be passed to 3. Here it is 6, so this is 6. So 1 and 2 along with 6 will be passed, and then it will be 3. Sorry, 1 and 2, 3, and we have an array sorted at the end is 1, 2, 3. We have an array of 1, 2, 3, and then both this left array and right array will be passed down to this. So from 1 to 3 will be one array, left array, and it will be right array for this. So eventually at the end of this we'll get an array here. Left array is 4, 5, 6, and right array is 1, 2, 3, and we want the final array to be here 1, 2, 3, 4, 5, 6. This will be compared, I will be here, J will be here, and it will be compared with this, the 1, 2, 3, and 4, 5, 6, it will be terminated. So at the end we get the sorting part. Okay, this is how this whole algorithm runs. So initially devise them, there is no assumption of how left array should be, right array should be. It's just moving forward with this particular flow of recursive algorithm of it, and at the end it put down to a place where this recursive part put down. Just took a time, took a pause, think about what was written. It might be complicated in the sense, but it's not complicated. We divide them and do recursively the same procedure again and again and again. That's how we are doing. So we took a merge sort of it. Then we call this merge function again. We're calling this merge sort again with this. Then we're calling the merge. For this is the merge sort, and here we're calling the merge. We divide them until m is not less than n, until 1 is not less than 3, 1 is not less than 2, 1 is less than 1, so we terminate at this particular point. So again doing with 2 and 2, recursively we are doing, and at the end we'll get particular part. So again merge, 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 and merge. This thing will be. Now this thing we can describe with, let's have this algorithm as, this can be taken down as, there's some properties now associated with this. First property is that we can say this is the tree type of structure coming from here to here. This is a tree, and uh, I'll not derive right now how the height of the tree can be find down, but let's say the height of the tree is log n. I described in some other video how this log n come down, but let's right now focus that height of the tree is log n. Now this, all this thing consumes some extra memory because you have to put this function call in some other one. This function KP is on hold until this function call is not completed. This function call is on hold until this function call is not completed. So this is some kind of dependencies are there from the first part to the last part. So this function need to be saved until some other functions are not get completed. So it will consume some extra memory. So recursive tree will consume some extra memory. So the recursive stack, we consume them as stack. Now it's not that if you just give a number of how, if we put this how many functions call we totally have for this 8 input or 6 input n equal to 6, if we how many functions call we actually have it, let's look it down. Let's mark it as number. So it starts with 1, then it is 2, then it is 3, then it is 4, 5, 6, 7, 8, then it is 9, then it is 10, then 11, 12, 13, 14, 15, 16. It seems there are 16 function calls are there. Okay. Now, at the any element point of time, we can have 16 defined stack. Stack, you know, the first come last out service of it. First come first out service stack. We come down to this. So we can have a recursive stack of it. But how is the size of the stack? So at the minimal point of time, we can have 16 defined stack. So we can view the stack as this particular way, where we have these elements are there. Whichever comes first, it goes out. So it's the first in, first out policy of stack. Okay. Now, in case of stack, now if it is a recursive stack, let's see how much memory it will consume to put this down. Now, initially 1 will be pushed in, then 2 will be pushed in, then 3 will be pushed in, then 4 will be pushed in. So you can see there is extra memory taken by merge, but at no point of time we actually, these are two different things, so it is not related to each other. Similarly, this merge is not related to this merge. So everything is independent, it is happening. So merge only at one point of time, if we take one full array, extra array of size n, that will be enough for that merge one. But for this recursive one, let's say how much size is needed. After 4, once 4 is completed, we can push 5. Once 5 is completed, we can push 6. Once 6 is get completed, we push them out, we push the 3. When 3 gets completed, it's size of 7. 7 gets up, it is 8. Even 8 gets up, it's 2. Then 2 gets completed, we can push 9 here, let's say on the same place. Now we add 9, again we push 10 here, and after 10 we push 11 out of here. Then at 11, then it is 1, it is 9, it is 10, it is 11. Then 11 we push as 12. After we complete 12, we push 13. We complete 13, we pushed out, and we 10 we now push as 14. Now 14 gets completed, we push 15. And 15 get completed, out of it we come out, and now at the 9 we push 16, and we after 16 get completed, we come out, we come to 1, and 1 get completed. So any point of time we actually require only this amount of space. Now for 6 it is 4. Now for other, depending on the input, it can be different. So that's how the height of the tree comes down to the particular picture. For the stack, so what is the space requirement is that? For the stack, the space requirement is order of log n only. This is the height of the tree. So that's the amount of space we require. So if we have 16, then we get 4. If we have 3, then just put the value and get that particular, how much extra space is required for this particular part. So the two properties is that for the merge one, we took an space of order of n, and for the merge sort of it, just for recursive stack, the extra space is order of log n. But for total space, if we talk about it, total space that is required by merge sort, because we both combine to a particular part, we actually have n plus log n, and dominating factor is n, so order of n. So big O of n. This is the space we require for this particular part of it. This is the space complexity that we talked about. Now, if we talk about the time complexity, I'll just go in very brief about the time complexity associated with it, because every algorithm is defined in a way that it should be useful. So how this is useful? Because one drawback that we have seen from the insurance short is the space requirement. So from the space requirement point of time, this is not good because it is taking some extra space. But in insurance short, we're taking only one part. Now let's talk about the time complexity of it. Now for the time complexity, let's see if this take an amount of time was, let's say for n element it take n t n of time to complete this. Now this is half part. For this is a constant amount of time it will take. For n elements it is taking tn time. For n by 2 elements we to the hub it take an n by 2 part. And for this it take as n by 2. And now at the end of merge it is taking order of n. Because we have seen the complexity taken by merge sort is order of n. As we talked about in the previous part of merge, how much time complexity is taken. So for n is actually taking 2 into t by n by 2 and order of n. This is the equation of time complexity that is required by the merge sort of it. This is the equation. Now we can solve this, but there is a rule from Master's theorem how we can actually fastly derive it of it from Master's theorem. I will discuss in another video how this Master's theorem come into picture, and from the Master's theorem we actually put down how much time it is required. So if you use the formula, you will come down to this formula of n log n. Now how this is came, we will discuss in another video of it. But just remember that the time complexity is required by this merge sort is n log n particular part. So these are defined properties. So out of place we discuss which is how it is time complexity, the space complexity, how this merging came into the picture. If we describe any tree type structure, it is good to actually visualize it into the particular part. But you can also use the array part of thing and do it particular part of it. So here we took the recursive stack and how each of the functions we pushed in, pushed out, how much space we required of it. Then we took an example. Before going to example, I took the example of here. If we took a simply, this was the initial example that we took, and then we relaxed them into some part and left part and right part are sorted. But initially, if we give this particular input to the merge sort, and then it will that particular thing that the assumption we don't need to put that particular assumption of it as we discussed in the particular slide. You can directly at the end it will give an sorted array of it. Then we previously we discussed about the merge algorithm. This algorithm we discussed in this particular example of it. Then we go to merge sort, describe each and every step. It is recursive thing. So this is a recursive procedure that has been called down. Previously we talked about the iterative procedure. In the insertion sort, again I'm saying there's no need of extra memory. In place algorithm, here we took some extra memory, but the time complexity is lower. So previously in the insertion sort, what we have is order of n squared. This is exponential. So exponential is very bad. If you have 100, it go into 100 square. So now, but in the this is the insertion part, but for the merge sort, the time complexity as I discussed is n log n, which is not exponential, but it is lower than the exponential. That's how the good part of the merge sort algorithms are there. Then these are things I discussed. Then after the next video, we'll discuss some other sorting part of it. If you have any doubt, just put in the comment part of it, and I will try to resolve it by replying to this commenting part. That's it. Thank you. I hope you learned something. For someone, it can be new. For someone, it's just a revision part that you have done.